All right, so for this problem, we have our old friend, our yellow material. So we're already told that our Young's modulus is equal to 1 GPa, our nu is equal to 0.4, so it's a polymer. We have our thermal expansion coefficient already. I'm going to go back into Mathematica. So let's go ahead, let's find these values, and let's get started on this problem. Looking at the values. So let's go ahead and let's take a peek here. So my y is equal to 1 times 10 to the 9. 10 to the 9. My nu is equal to 0.4. My alpha is equal to 8 times 10 to the minus 6. Our del T is equal to our final temperature minus 100 minus 25. And we're told basically, yeah, we go from room temperature, bond of the blue walls, room temperature, and then now we decrease our temperature further. So what is going to happen here is when we look at our strain tensor and stress tensor, so stress is this, strain is this. So when I decrease, I'm bonded to the blue wall. So my 2,2 is 0. I'm going to have some strain in the 1,1. I'm going to have some strain in the 3,3. They should both contract. I'm going to have stress in the 2,2, and I have nothing else here. And same thing. So I have 3 unknowns, but I can write my 3 equations. So my E22 is equal to 0, my sig11 equals 0, my sig33 equals 0, and I can now solve my series of equations, E11. And remember, so it is going to be equal, set equal to 1, I'm going to do my ET, E thermal, not phone home, is alpha times del T, and you can see that value here. Makes sense, negative, fantastic. So now we can start to go and solve this problem. So y sig11 minus nu times sig22 plus sig33, and do that, and then E22, blah, 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 blah. So we all know. We know the story from here, equals sig22, E22, sig1, and then finally, let's do the 3, 1, 1. And so we are now looking to solve these equations for E11, sig22, E33. But that doesn't work because we need to put plus ET, we need to do plus ET, and we need to do right here plus ET. And now we've got our values. So E11 is this, sig22 is this, really the only value I really care about, and E33 is this. Makes sense. Fantastic. Negative, they should be contracting. So this is the stress that I basically am applying to this material. Additionally, I'm given surface area values, strain energy release rate, and the stress intensity factor is 5 MPa. So and the material is actually the red curve I see below. So the red curve has a sigma y. So my red curve, let's just say sigma y is about 500 MPa. So I'm going to write that down right now. So sig y is equal to 500 times 10 to the 6. I'm also given that my gamma is equal to 500. My strain energy release rate is 87. GC is equal to 87. And finally, my K1C is equal to 5 times 10 to the 6. So, fantastic. So I've got those values, and now I'm asked, will this material yield based on any of our criteria? Well, if I'm just looking at general yielding, actually, again, what criteria should we pick? Ranking? No. We need to make sure our sigma 1 minus sigma 3, so which basically still this, is sig22. Is it greater than sig y? Nope, so it will, or it should not yield. What would be, or actually what is the radius of our plastic zone here? Well, we actually have that equation. We've gone through that already in our notes previously in class. So my RP is just going to be equal to my basically my K1. But my K1 not my K1C, my K1 is going to be equal to basically sig22 times sig22 times square root of pi times a. So that will be my sigma 1. Actually, that value here. So our p is equal to ki squared divided by 2 times pi times sig y squared as well. So this would be my radius of my plastic zone given some initial crack size. What is the minimum crack size that will cause fracture for this problem? So I could solve that using, again, you could use actually quite a variety here. K1C is set equal to f, which is just going to be sig22 times square root pi times a. We could actually contrast these answers, so that's a pretty big crack size here for that value. Again, we're not yielding the material. I could also analyze this by looking at, I could solve as well, sig22 set equal to square root. Again, assuming, because again, this is a plastic, so I could use my OR1 expression. So my Young's modulus times GC divided by pi times A. So I could also find that as well. Oops, come on, pick that up. And again, different values, different parameters, because again, I'm making these problems up. But anyways, yeah, that's pretty much it for this problem. So make sure you use the kind of that plastic zone equation. Make sure you kind of see which material we're working with, and we can kind of solve and finish up these problems. Excellent. Thanks. And let's go to now number 2. All right, so let's go ahead and look at number 2 now. So I'm looking for the stress curves. I'm interested in blue, red, and green. So let's see. Let's get my colors ready to go. Blue's not exactly that color, but actually let's do more colors. Oh, come on, I need some better blues. Come on, notepad, be better. How about that bright blue? Let's just take what we can get. All right, so looking at this curve, or looking at these 3 curves, I know that my yield strength of green is greater than my yield strength of red, which is greater than my yield strength of blue. I also see that they pretty much have the same slope. We'll kind of look at that later. So, which creep deformation mechanism corresponds to which material? Explain and fill out the regions. So my green is the highest, then red, and then blue. So I know, and actually we could just fill out the regions right now. Let's see if I can, I'll change this color to, let's change this to black. Let's change it to purple. So I know, we could kind of zoom in here. Zoom in. I know that this is my theoretical yield strength. Why? Because it's sigma over g is basically a tenth, so that is our theoretical yield strength, TS. This is our dislocation glide, dg, dg, dg. This is going to be, again, height, PLC, power law creep, power law creep. This is going to be my cobble. This will also be my cobble. This is going to be my elastic, elastic, elastic. And finally, I have my NH, NH, and NH. So, looking at these curves, I could look at the yield strength here, here, and here. So clearly I see that the highest yield strength, which I believe, let's go back up here, green, red, blue. So this must be my green. So green, then it's my red. Where's my red? Red, and then my blue is right here. So I can look at it just by looking at that yield strength. So we've got those values. Now for number 3, and that's pretty much it for number 2. Explain, fill the regions. What strengthening mechanism can be occurring for these materials? So we have all of the same yield strength. The same Young's moduli approximately. So what could be occurring? I could have, basically I could be looking at work hardening. So my change in yield strength is proportional to rho to the 1/2. I could be looking at grain size strengthening, which is related. So dg to the -1. And that's pretty much it. Precipitate strengthening, and then the our solute strengthening will kind of slightly change that Young's modulus, but I could have some small, I could possibly have some small solute strengthening occurring here. But looking at those values, I'd say predominantly these are 2 really good answers. And again, we can see that why, if I'm grain size strengthening, or if I'm increasing if I'm grain size strengthening, for example, I could see that my blue curve has the smallest cobalt creep region. So if I were to rank, the DG of my green is smaller than the DG of my red is smaller than the DG of my blue. And we can see that because our cobalt creep region, which scales as DG to the -3, that is shrinking as we kind of decrease that yield strength. So, excellent. Turns out my undergraduates measured the ratio of the area of the grain boundaries to grain size and found values to be 0.01, 0.001, and here. Which curves could these values correspond to? All right, so looking at, okay, the ratio of the area of the grain boundaries to the grain size. So I'm looking effectively at that value that we looked at in class. So if we remember, we looked at approximately how we could kind of relate that area. So this value is essentially the width, 2 times the width of our dislocation core, or basically the width of your, or excuse me, not the dislocation core, the width of your grain boundary over your grain size. So if this value is small, it means my grain size is very, very, very large. If that value is larger, then we know that this is larger. So essentially that we have, basically, or you can kind of think of it as a smaller grain size as well. Because this value is effectively not changing. This value is always going to be, as we kind of talked about in class, on the order of, basically a nanometer or so. So it's going to be around that nanometer, maybe 5 nanometers at the most. So really this is the value that's changing. So if this is getting small, or if this value is getting large, our DG is getting kind of smaller and smaller. So we know what curves could these correspond to. So we know DG here of my green material is going to be my smallest. So the smallest here will lead to the largest value. So this would be, basically, let me erase here. So smallest value of my grain size would be the large value here. So this could be my green, this could be my red, and this could be my blue. There we go. We got it. Excellent. So now we could go ahead and start to work on basically this value for, actually, we could start to look at some of this fatigue problem. So let's go ahead and zoom out here. So I just completed work on Boeing 737, engineer ultrasonics test resealed micro cracks. So I have an A0 that's on the order of 1 centimeter in titanium. So I'm going to say my Young's modulus is equal to 100 GPa. My nu is equal to 0.3, just like we did in the old days. So the supports are under a stress during a tensile stress during flight. So the stress applied, or stress max, is equal to 100 MPa. Fracture toughness, K1C is 100, blah, blah, blah. Yield strength, Young's modulus. I'm going to ignore this Young's modulus. You could solve it if you want, but we want to do metal. For the outlet, the applied stress is cyclical, and the fatigue is a concern. So how many cycles can the Boeing 737 make before failure? Here, R is equal to 0, and C is equal to, N is equal to 4. Should we cancel the flight? So we need to take a look at our expressions. So specifically, we need to see what our values. So if R is equal to 0, R is equal to sigma min over sigma max. So if this is equal to 0, this is saying sigma min must be equal to 0. So our sigma max is this sigma applied. So that's equal to sigma max. So if I have those values, I can now start to solve and actually plug into my equations. So let's go ahead and let's look back at our expression for our number of cycles to failure. So let's look here. So I've got my A0 equals 1 times 10 to the minus 2. My C in this problem is equal to, so a big C is equal to 10 to the minus 24. And then, what else do we have in this problem? We're saying that M is equal to 4. M equals 4. And what else do we got? We're going to assume that our F is going to be equal to 1. We're going to assume that our del sig, which is this different sigma max, is just going to be 100 times 10. Oops. 100 times 10 to the 6th. And excellent. So we could start to do our number of cycles to failure is equal to 1 divided by C times, 1 divided by F times del sig times square root of pi, all of this to the m power, and then our big C is here. Whew. Let's get that one. All right. Then we're multiplying this by a sub c to the 1 minus m divided by 2 minus a naught to the 1 minus m divided by 2. And we can go divide all that by 1 minus m divided by 2. So what is our a sub c, our critical a sub c? Well, our a sub c, we could solve that. We're given, essentially in this problem, that K1C is equal to 100 times 10 to the 6th. So I could solve now that K1C is equal to F, double equal, F times del sig, F times del sig, and then we can go ahead and solve. We can solve for our critical crack, length. So del sig times square root pi times a. Solve. So that's our critical crack size, a sub c. So our AC is equal to this. So we could see our initial A naught. Let's look at this. So we still have some values to get to. So I can now say that A sub c is this, and now we can do that. And it's not going to take too much to get to there. So essentially that's going to be our value, our number of cycles to failure. Excellent. All right, on to the next problem here. So should we cancel the flight? Absolutely. All right, everyone, so now we're in the last problem. So let's take a look at the stress strain curve below. Which strengthening mechanism can be occurring here? So now we see slightly different slopes. So we could be seeing our solute strengthening, C sol to the 1/2 power, or we could be looking at our yield strength equation for this, and then like that, for cutting and precipitate, basically precipitant strengthening. So adding precipitate particles, and we know that I have two contributions here. I could either cut or I could bow. If I cut, I am creating surface area, so that's my energy penalty. So I don't want to cut large particles because that's more surface area. I want to cut small particles. Or my dislocation line can bow around the particle, so basically bowing around it and then basically creating that dislocation. So precipitate dislocation line approaches and it curves around. So bowing is curvature, so 1 over radius is my kappa. So I want to reduce that curvature energy penalty, so I want to bow around large particle sizes. Excellent. List scaling, all that other things. If precipitate strengthening is occurring, how will critical radius of Boeing be affected by increasing the volume fraction of particles? So if I increase the volume fraction of my particles, and if I cut, I'm creating more surface area. So if I increase that, this critical radius, this R sub c, is going to decrease, shift to the left. If I decrease my precipitate sizes, it'll shift to the, or if I decrease that volume fraction of particles, so VP increases, RC decreases. VP decreases, RC increases. Excellent. That's it. Problem set 7. A nice one that's to do. So study well for your exam 3, and I will see you next time. Thanks. Bye.